going to talk about Ethereum accounts, addresses, and private keys. So I'll talk about how a private key is generated and what the private key is. I'll talk about how the Ethereum address is derived from the private key. I'll talk about how a private key is used and how digital signatures work. I will talk about how a hardware wallet might fit in here and how the hardware wallet can hold the private key and do the digital signing. And then I'll talk about where Metamask fits into all of this and how Metamask can be used to create and propagate the transactions, but should maybe not be used to hold your private key. And I'll talk about all this in some technical depth because I think if you actually understand what's going on under the hood, then everything becomes much easier. If you follow tutorials, then tutorials present you with a track, a path that you have to follow. And if you get off that path, then you're lost. Whereas if you actually understand how the thing's working, you never get lost. And this all becomes much easier. So here I've got Etherscan, and Etherscan is fantastic. Etherscan is, I use it as my source of truth for all things happening in Ethereum. So if I do a trade on Uniswap or SushiSwap, or I do anything on the Ethereum system, I go to my account, I search it in here, or I bookmark it. I go to the account and I just see if the transaction's there, if it's being processed, et cetera, et cetera. Sometimes, often, people will use Metamask, and they'll do like a swap, and then they'll look in Metamask to see if their token that they just bought is there, and often it's not, and then they panic. And I always say, just use Etherscan as your source of truth. I'll explain in another video why that happens and how to check account balances in a more reliable way. But anyway, Etherscan is great. This is just the main page. So here is an Ethereum address. This is one of Vitalik's addresses, vitalik.eth. And it's got 4,300 ETH, $12 million, bunch of tokens. And, Ethereum accounts, like it's kind of self-explanatory. You can think of an Ethereum account like a bank account, kind of. It has your ETH, it has your tokens, it has your NFTs, and it's pretty straightforward. The account has an address, and the address is here. So note the 0x at the start. This is not really part of the address. This is a prefix denoting that this address here is being displayed in hexadecimal form. So with any number, you can display it in a bunch of different formats. Like I can define by the way, this is just Python, a Python little terminal here. I can define a number. I can, so in hex, that's the representation of that number, 3,434. You can represent it in binary. These are just different representations of a number. So anyway, this Ethereum account, it consists of these hexadecimal characters. And how much data is there in that account, in that string? So we can figure that out. Define the address as a variable here. And how long is it? It's 40 characters long. So this address is 40 characters, and how much data is there in each character? Well, it's hexadecimal. Hexadecimal goes 0, 1, 2, 3 up to 9, and then A, B, C, D, E, F. So there's 16 possible values for a hexadecimal character. And if we want to figure out how much data that is, it's, 16 possible values. 2 to the power of 4 is 16. So you need 4 bits to represent a hexadecimal character. Okay, Great. Now there's 40 characters, 4 bits, 160 bits. So the address is 160 bits. That's 20 bytes. That's all fine. But, okay, so we have this 160-bit address. Each Ethereum account has a different address. But where does this number come from? How is the address created? So it starts with the private key. And here I will show, how you could create a private key. So the private key is a random number. And the key thing is that this random number needs to be generated securely, because if anyone finds your private key, if it ever leaks out, you will likely lose everything in your account. So the private key is the key. If you think of an Ethereum address as like a sort of like a safety deposit box in a bank, then the private key is like the key. It is the key. And if you lose the key, you lose everything. So this is what a private key looks like. So the private key is just a really big number. It's a really big, we can represent that in binary. So this is the private key. And this is like the fundamental backbone of security of all of these crypto systems, and how cryptography is secure generally as well, is you just have, in this example, this key is 256 bits. So maybe I should have mentioned this. By the way, this is just the random library in Python. I'm producing a random integer, and that integer is 256 bits. So that's what this range is illustrating or indicating. So this number we've produced is, it's somewhere in that range of 0 to 2 to the power of 256 minus 1. And this is its representation in binary. Now, like I said, this is the security of the system. If you could, if you can guess one of these private keys, like just write a program to generate a bunch of these private keys and then derive addresses, which I'll show how we do in a second. And if you happen to hit on a private key that has an address on Ethereum that has some assets in it, then you can steal them. But it's really hard to do that because this number is actually really large, and this range is insanely large. Like all the computers in the world for like a zillion years, you won't be able to find a private key that works. So yeah, we've got this big private key. This is just a randomly generated number. Now, with that private key, we follow these steps. We'll take the private key, we'll do some transformations on it, and we'll get an address. And more specifically, so this is from the Ethereum yellow paper. This is like the white paper, but more technical. And this is how this expression here is showing how an Ethereum address is created. So the address A takes an argument P sub R, which is the private key. So the way you get this address is you take private key, you run it through this function, this ECDSA pub key thing. And what this is doing, this is public private key cryptography, which is widely used outside of cryptocurrencies. And you give it a private key, this big number, and it will produce, using some fancy math, it'll produce a corresponding public key. Now these two numbers, this public key, private key, have this association with each other, where you can take your private key and you can digitally sign data. So any data, like it can be just a word or it can be a big chunk of like a megabyte worth of data. You can take that data, use your digital signature, or your private key, and produce a digital signature. Okay, so you have the payload, your private key, and you use that together to produce a signature. The signature can then be the signature you just broadcast out into the world along with the data that you've signed. And then people anywhere can take your public key, which you've also broadcasted or is associated with your account, for example. They can take your public key and verify that that signature is legit. They can verify that that signature was produced by someone who has that private key that matches up with that public key, and that signature was created for that specific chunk of data. So if you change like one bit of the data payload, the signature won't match anymore. And if you can't, with a given private key, you can't sign some data for someone else's public key, So this is producing the public key, and then to actually produce the Ethereum address, because we don't use the public key as the address. And I'm not 100% sure why. I think you could. I don't think there's any reason you couldn't, although this public key might be a bit too big. I think it might be 256 bits. But anyway, we take the public key and we run it through a hash algorithm, Ketchak 256. And this is just a hash algorithm, just takes any data input and produces what can be thought of as like a signet or like a fingerprint for that data. So any data you input will produce a fingerprint of a fixed length. So every data input will produce 256 bits, and each data input will produce a different 256-bit hash. But if you input the same data, twice, you'll get the same fingerprint, right? And so yeah, we take the public key, hash it, and then simply take the rightmost 160 bits. 160 bits. Take the rightmost 160 bits, so that's bit 96 to 255. And that is how the address is created. And now, so your address is publicly known. Everyone can see it. The private key is obviously private, it's hidden. But when this, when a transaction is created, like this one, the other nodes in the network can look at the transaction data and verify that the signature associated with that transaction was in fact created by the private key, which matches to this address. And I just said that the address is not the public key, but that's fine because there's a way to derive the public key. So this, I don't know exactly the math here, but an Ethereum transaction includes these values with the signature data, VRS, and S, I believe, is the signature. These other two pieces of data allow you to derive the public key. So the public key is not strictly included with the data, but you can derive it using the signature data that is included. And you can, given all this data, you can verify the signature on the transaction, and then it gets mined. And that's how it works. So how does like the hardware wallet fit in here? So a hardware wallet has the private key on it. A hardware wallet, when you set up a hardware wallet like a ledger, you'll set it up, it will generate a random number, a random private key on the device, and it'll give you the seed words, right? Like if you've set up a ledger, you've probably never seen a big random key displayed to you. But what it will do is it'll give you a bunch of words and, gives you a big list of words. And these words are essentially the private key, which is why they tell you to be extremely careful with the words. The way this works is you basically just take and, for example, here's the private key. Maybe you say each 4-digit chunk, we'll just map that to a word. So we'll say let's say we have this number, 1339, we'll just map that to cat. And you build up this big library with, in this case, like 10,000 words, common words, and you just map a value to each word. Doesn't really matter how you do the mapping. You can publish this mapping, this dictionary, widely. That's fine. And then you just generate the private key on the device, and you show the user a sequence of words, like 20 words or whatever. They write down the words, and that is essentially the private key. And the reason you do that is just easier. If you set up your ledger and it wanted you to write down this huge number, then it'd be very error prone, and it's much easier to write down words. So then what a hardware wallet does is it holds your private key and it will sign the transactions. So I'll show you a bit about how this flow kind of works. So when you're on, let's say you want to do a swap on Uniswap, you request the front end. So you go to like uniswap.org and your browser is making a request for the JavaScript, HTML, CSS that represents the Uniswap page, right? Now, there's multiple ways you can get this front end. You can download it. You can get it from GitHub. You can get it from a server, which is the way we usually do it. If you just type it in the browser, it's hitting some server. There's also options like IPFS. But anyway, you get the front end. Now you fill in the swap that you want to do. You hit swap, and your browser will hit typically Metamask. Metamask is just the most commonly used kind of wallet software here. And so what it'll do is the front end is taking this data you've inputted, and it will construct a like partial transaction, like the details of what the swap is you're doing. It sends that to Metamask. Metamask knows what account you're planning to do this transaction from. So Metamask can fill in more data. Now at this point, let's assume you've done this, you have it set up the right way, which is to use a hardware wallet with Metamask. What you then do is so Metamask will like finish constructing your transaction, but it's not signing it, right? So if you have your hardware wallet set up with Metamask, then Metamask will take that transaction you've constructed and send it to the hardware wallet, and the hardware wallet will actually sign it because the hardware wallet has your private key. In this kind of setup, MetaMask does not have your private key, and that's what you want, because MetaMask is a browser extension. right? So this, if I have some account here, like this account here, I've never used. It's just a random MetaMask account. And this account has a private key, of course. And where is that private key stored? Well, MetaMask at some point generated it, and it's in a directory somewhere on my computer. It has to be, because MetaMask needs it to sign stuff. So it's no doubt encrypted and password protected, but in order for MetaMask to actually sign anything, it has to have that actual key. It has to decrypt it. So it has to be in memory somewhere. And I mean, that's just scary. Having your private key just on your computer is scary. And people get hacked all the time. So the better way to do it is to have MetaMask serve only as this intermediary where it creates the transactions, then sends it to the hardware wallet. The hardware wallet signs on device, right? So it never bounces the private key out to MetaMask or anything like that. It receives the data, it produces a signature, it sends the signature back to your computer and back to MetaMask. And now it's good to go. And MetaMask can simply broadcast that transaction, because the transaction ultimately has to go to computers in the Ethereum network, and then they mine the transaction, and then it's done. So how does an Ethereum account get registered on Ethereum? And this is actually an interesting thing, is if you random address, yeah. So here I'm going to generate a random address. So I've literally just generated this without a private key or anything. I've just generated a random hex string. So this is 160 bits, but it's just random hex, right? Now I can take this and go to Etherscan, and boom, there's an address here, there's an account here. But that's doesn't make any sense because I literally just created this. I could randomly even change one character, change the 6 to a 7, and we have another one. So these addresses that I've just created, that I've just made up, they don't actually exist, so to speak, on the Ethereum system. If you run an Ethereum node and you go through on that node, you look through all of the accounts that are like in that database, you won't find this address. And so the way that Ethereum accounts are created is you can generate your private key however you want, and you can derive your associated address from that. But until some ETH or a token or something is sent to this address, until something's done with the address, it doesn't exist, right? So the moment you actually, you can create a bunch of these addresses offline, you can have the private key and public key, but until you send something to them, they're not really created. And the moment you do send something, they become real. So yeah, that's pretty much it. Hope that's somewhat helpful. Let me know if you have any requests or if that makes sense. Yeah, I'll be doing a video soon on how tokens work, because there's a lot of misconceptions there. Tokens and NFTs, and why do your tokens never show up in MetaMask, right? Why does Ledger Live never seem to show the right tokens, or even Even Etherscan, sometimes you buy a token and it's just not there. Why? I'll explain that next time. So thanks for watching. See ya.